Hi everyone, this is Mo, and today I'm going to talk about a cool topic that can enhance the security of your app, your website or software, drastically. And that can actually prevent all kind of password breaches and those kind of incidents you hear on news, right? So traditionally, as software engineers, software developers, web app developers, website developers use databases or file system, mostly databases, in order to store user password and fetch them through SQL when they try to perform, authentication, right? When they try to authenticate. So imagine a way that servers actually knows you or knows your users without storing any data, without even seeing their password. So that would be, great, right? Because it prevents that password breaches and enhance the security of the entire ecosystem. So it sounds impossible, based on traditional, de facto ways like using SQL approaches. However, there is an approach for that. It's possible, and this is possible through zero knowledge proofs. So in this video, I'm gonna briefly introduce what is this technique, and we are also going to have a demo in Rust and explain you how it works in practice. But before we continue, if you like this kind of content and my channel, please right now subscribe, give it a like, and also at the end of the movie write your comment. I really like to hear your comments, and please subscribe. That encourages me to actually create more niche and useful content for you. So let us stay tuned and do it together. Alright guys, let's do that actually in Rust. So we use cargo and we create a new project. We call this zk proofs demo. And now we have this structure here. So we are going to actually add a dependency to our project for randomization. So I'm gonna use rand, and because of that I need to actually update my cargo Tamil file. So I use nano, and over here I'm gonna use rand. I use version 0.8 and I exit this one. So I open a terminal here, and in my terminal I need to have like 3 main modules. I go to the src, to the source folder, and over here I create one module. I would call it simple zk proof. It's much easier for me. And the other file I'm gonna make zk comparison, and I am going to make also zk vulnerabilities. I explain them later actually one by one. So the files are ready. I have the files. Alright, so in this module, simple underline zk underline proofs, we are going to implement the schnorr protocol. We are going to do that for implementing the discrete log zero knowledge proofs. This is actually simple but very powerful. For this, first we need to make a struct, to hold the prime module, and then generate, and so for this actually we create also a structure, but first I use actually rand for the randomization. Create this struct. I call this simple zk proof. And here this struct actually is to hold the prime modules, like generator, secret value, and also public commitments. And we have here p 4. We don't need all of these guys. We have q. We need secrets. X, and then we have edge. good to go for this. And then we need to actually implement three main functions, set of functions that actually compute the public value g power x mod p, and then we need a proof function that generate the commitment challenge response triple, and then we need the verify function that actually is responsible for checking the proof equation without actually learning the secret x here. So let me actually, yes, so now this is ready. Guys, so we are done with the zk proofs. We have our basic structures, and now I'm gonna actually talk about zk comparisons. In this module, I'm going to actually make a framework to compare zkSNARK and zkSTARKs in terms of their trade-offs, and for that, I actually make a comparison struct, which method that return the map for each system, and like covering proof size, verification time, trusted setup requirements, and quantum resistance. And in a brief, SNARK or zkSNARKs mostly prioritize, efficiency with small proofs, but they require a trusted setup, And on the other hand, zkSNARKs mostly sacrifice the size for transparency and quantum safety. So that's in a nutshell about the trade-off. So let's actually start coding this module. Gonna use std here, collections, hash maps, and then I'm gonna actually create my struct. Yes. All right. So it's good to go. Later we come back and test them all. All right, so now in the last module, vulnerabilities, we are going to show actually for zk proof systems how they can actually have weak implementation, which is also possible, and this possibility actually can break the production code, and it can actually cause system to get hacked and compromised by attackers. So the point I'm trying to make here is, if by using zkP doesn't necessarily guarantee the safety and security of your system. You need to have a proper secure implementation of that. Otherwise, it can actually cost a lot, because this kind of system usually are used nowadays in decentralized distributed systems like blockchain for DeFi protocols and mixers and places like that. And actually, any bug here can be quite devastating, So let me actually demonstrate that how we are going to do this. I am going to make a struct here that has some static methods, let's say 4 static methods, and I'm actually going to show the soundness break, how it can actually break, how trusted setup can have issues, a function for circuit bug, and also a function for security checklist. So let's go and implement these codes, one by one together. I make a struct first here and put the stuff actually. Right. All right. Now it's time to compile our modules and run the demo. So I actually now first use cargo build to compile our modules and see if there is any errors. So everything is fine. I can also have a tree here. Now I use cargo run to execute the modules, and then I explain that one by one to you. So here the first module we have, you can see the implementation of the. So in this module, you can see the implementation of a Schnorr protocol in action. So we have a secret X, which is equal to 7, and this is actually generated a public value in public value h, which is equal to 17, as you can see here. So the proof actually gets generated with a commitment, challenge, and response. And after the verifier confirms it's valid without even learning the secret itself. So zero knowledge proven here. And for module 2, here we have the comparison between zkSNARK and zkSTARKs. And SNARKs are, as you can see, quite tiny, just 200 bytes, and fast, but they need also that trusted setup, in place. STARKs, on the other hand, are bigger, 100 kilobytes, way more, basically larger, and slower, of course, but they are transparent and quantum resistant. So for your protocol which one must be based on your network and users and environment, you can actually decide about that. And over here we do have the security vulnerabilities that shows, although you can use zkPs for your security and your safety, if you are not really familiar with proper implementation of that, you might actually introduce bugs and vulnerabilities to your system, which is not fine. So the first one is a weak challenge space. So with only 8 bits, there are just 256 possibilities. So what does it mean? It means an attacker can actually perform brute force attack, maybe less than a minute, and it's not difficult to actually break it down. However, if you have like 256 bits, then computational is impossible to break it. It's very difficult. The second challenge is about trusted setup. So if the trusted setup compromise, for example, an attacker can get the toxic waste from a SNARK setup, then it can mint unlimited coins, and for example in a blockchain network, and the attack can completely become undetectable. So this is why Zcash, for example, Zcash is a blockchain technology for private transactions. That's why actually it uses multi-party ceremonies here to get around this issue. The third vulnerability is about circuit implementation bugs, which is also very common between devs, and they might make this mistake. So the circuit checks if the balance is greater than amount, but there is no check that amount is positive here, right? So that means an attacker can set amount to let's say negative 5,000 here, and then the check pass, and the key they can actually mint tokens instead of withdrawing. So this bug can cause a lot, in especially in like a blockchain, financial, DeFi kind of environment, and any other environment that actually use this technology. So yeah, in conclusion, here was the complete analysis. I hope you find it useful. It shows how zk proofs work in action. You can compare them between two major ones and how they break. And if you're building a zero knowledge proofs, it's important to understand these vulnerabilities. I hope you like this video. Please don't forget to write your comment, like, and follow. And we are performing security implementation and analysis at ByteScan.net, and you can also follow me on LinkedIn, GitHub, and other social media. I list them in the description. So yeah, I hope you enjoyed that, and see you next time.